Did you like the sign? If you've been here before, you know we open every show with that. Those are fluorescent light tubes. At home in your electrical fixtures, you turn the power on. A strong electric field is generated. The gas molecules are excited. When they drop back down to their lower energy state, the energy they give off causes the tube to fluoresce or give off light. Here, they're not hooked up to anything electrically. We just tie them to that piece of wood. We use a Tesla coil to generate that strong electric field. The field is so strong the air around the Tesla coil breaks down and becomes a conductor. And that's what lightning is. So we made a little bit of lightning today. Welcome. Welcome to the Physics Show. The community around Foothill College is so supportive of the college. We appreciate it very much. We're so happy we can put a show like this on for you. I'd like to start out by asking you a question. If this is your very first time to a physics show, give yourselves a round of applause. All right, welcome. Welcome. And if you've been to one or more shows in the past, give yourselves a round of applause. Okay, welcome back. Welcome back. This is the physics show, so I have to tell you what physics is all about, right? Well, you're in school, you learn all kinds of wonderful things. You could almost put those things into different categories, right? Your reading and writing, your history, your math. One of those categories is science, right? Give it up for science, yeah? And even under science, there are so many things. We put those into different categories. You've got your chemistry and your biology and geology. One of those categories is physics. That's right, physics. And physics tries to explain the world we live in. Physics tries to explain the world we live in. Why the sky is blue. Why the backpack slides off the seat next to you onto the floor when the car stops suddenly, right? Sound, light, lots of different topics in physics. So we could break that up into many topics also, right? Last year we talked about light and sound. This year we're going to talk about inertia, temperature, and pressure. Maybe next year we'll do electricity and magnetism. I like to say physics is a journey, and we're very happy that you're coming along with us on that journey. Let's get started by introducing the folks that are going to be presenting with me on stage. My friend and colleague, Foothill physics instructor, David Marasco. We love to show off our students. We have a couple of students on stage with us. Haley Miller. And Olga Kritova. I'm Frank Coscarano. And you know what I always say, if you can't have fun with physics, you aren't a very fun person. So let's get started. Let's have some fun. We're going to talk a little bit about this gentleman, Galileo. He made all kinds of contributions to science about 400 years ago. We're not even going to touch on all the contributions to astronomy and the things he did as a mathematician and an inventor. We are just going to focus on a few things he did for physics. And one of the most important ideas that he contributed to physics is the idea of inertia. And it's said he got the idea by setting up a ramp like this, a plane, and he released a ball on a real low friction ramp, and it rolled up the other side to about the height it started from before it momentarily came to rest. And he thought, well, what would happen if I bend that down so it has a much longer distance to travel up? How high up the other side is it going to go? And it turns out it goes up that much longer distance to about the same height it started from. And then he thought, well, what would happen if I bend it down so it's flat like this? That ball is going to keep going forever. And that is correct. This idea of inertia, when something is at rest, it is going to stay at rest until a force acts on it and causes it to move. And when something is moving, it's going to continue to move until a force acts on it and changes that motion. And we were stuck thinking about things the wrong way, and not much progress was made in physics before this idea came along. Why were we stuck thinking about things the wrong way? If I push on this box, is it going to keep going forever? No. Why does it stop? Because something pushed back on it and caused it to stop, right? The friction between the box and the floor. David, is there some way we could greatly reduce friction? An air hockey puck. This is going to float on a cushion of air. Oh, look at that. It keeps going and going. Oops. until it hits a groove in the stage. So you can see this looks like it could keep going and going and going, at least until the batteries run out. But you get the idea. If we can reduce friction, then, oh, maybe we get the idea. Maybe that object will keep going and going and going. And so once that idea came out, all kinds of progress was made in physics after that. Let's start out with a simple demonstration on inertia. Maybe you've done this. You have a ball and a wagon. I'm going to push the wagon that way. What's the ball going to do? You ready? Here goes. What did it do? Maybe this will help. The ball is right here. Okay, the ball is right here. You ready? It actually moved forward a little bit, didn't it? Because it didn't have a choice. The wagon was pushing it that way. But it resisted that change in motion. It has inertia. It resisted that change in motion. The wagon didn't have a choice. I was pulling on it, right? But the ball lagged behind with respect to the wagon because it has inertia. How do we know the ball has inertia? Because it's made of stuff. It has mass. It has weight. And the more mass something has, the more inertia it has. So even you and I have inertia, but I probably have a little bit more than you do. Okay, so now let's get the wagon moving, and let's see what happens when it stops suddenly. What did the ball do? It kept moving, right? Until something, the front of the wagon, acted on it with a force and stopped it from moving. And the same thing happens to us, you and me, when we're in the car. Our bodies have inertia. We want to keep going when the car stops suddenly. We don't want the windshield of the car to be the thing that stops us, do we? That would be bad, right? What do? We wear a seatbelt. So then what happens? The car stops suddenly, and the basketball and us were held in nice and safe, right? So please, always wear your seatbelt. Now the wagon here, it has inertia. It's made of stuff. It has some weight. But you know, the empty wagon, it's pretty light. Doesn't have a lot of inertia. Right now it's sitting here at rest, and it's going to stay at rest until a force acts on it and causes its motion to change. So I'm going to exert a small force on the wagon. Let's see what happens. So a small force caused a big change in motion because the wagon doesn't have very much inertia. Now, if we could magically increase the inertia of the wagon by adding some kind of a massive object to it, safety first at the physics show. And I exert the same small force now to this massive object. It hardly has any effect, right? To get the same change in motion for this big massive object would take a much bigger force. That's the idea of inertia. Now let's see what happens with a hammer and an anvil.
Here's a hammer. It's pretty heavy, it's got some inertia. So when I swing the hammer, it wants to keep going. And if I had wood and a nail, I could get the hammer moving real quick. It'll keep going through the nail, and it'll nail the nail into the wood. But I don't have a nail in wood. I have my hand. So if I get it going real fast, it's going to want to go through my hand, and that's going to hurt a lot. But if I'm thinking about inertia, I can get something with more inertia, something really heavy like this anvil. If it's sitting in my hand, it wants to stay in my hand. So I get the hammer moving. The inertia of this saves my hand from getting hurt.
So what we're seeing is that all of these objects have mass. That means they've got inertia. That means that if they are at rest, they want to stay at rest. Now, on this table, we've got a bunch of stuff with inertia. We've got a tablecloth. We've got a fork, we've got a plate, we've got the cookie, we've got a glass. And at the physics show, if we're fancy enough to bring in a tablecloth, you know we're going to have a candle. Now, all of this is at rest. It wants to stay at rest, but Frank is going to get that tablecloth moving. We love to count things down at the physics show. I'm going to need your help. 3, 2, 1. Now, kids, should you try that at home? Parents, should the kids try that at home? Science is for everybody. So we should all go home and try this experiment. But first, we're going to listen to Frank. He's got some advice.
I guarantee the first few times you do this, maybe more than that, whatever you're doing it with, it's going to go flying onto the floor. So I like to use a piece of wood, just a little block of wood like this, or any piece of wood is good. Or sometimes a book. A book works well. I don't know if you can see that, but if your book is about Galileo, it works really well. And always ask permission first.
So kids, do eggs have inertia? If they are at rest, do they want to stay at rest? All of these things here, the glass of water, the pie plate, the cardboard tube, the egg, they all have inertia. They are all at rest. They want to stay at rest. But Frank is going to get some of these things moving. What you got there, Frank?
Got a broomstick.
What you going to do with it?
I'm going to whack that pie plate. You ready?
Let's count this down. 3, 2, 1.
You understand what I'm doing here, right? Gonna hit that pie plate. It's gonna go flying toward David. We'll keep our eye on the egg.
3, 2, 1. Now, Frank, should the kids try this one at home?
Yes. But you don't have to get eggs and pie plates. Our graphic here shows you just a piece of cardboard and a quarter or a nickel, some kind of coin. Give that cardboard a flick with your finger or use a pencil to flick it out of the way. That's the same demonstration. And of course, if you really wanted to use a pie plate or something, you don't have to use eggs. Just a small ball, like a bowling ball or something.
Bowling ball, that's a golf ball.
A golf ball.
Yeah, no one uses a bowling ball. Bowling ball's crazy.
You couldn't possibly use a bowling ball.
That would be impossible. No one could do that.
Or could you?
So you guys see what we're doing here, right? We're just supersizing the experiment. This is my big glass of water. Except for water, we have foam. This is my pie plate, just some wood. And this is my big egg. It's a bowling ball. So I'm going to assume position. And are you guys going to count with me? 3, 2, 1.
This is also a fun demonstration. We get a bowling ball. We'll hang it from a string, and there'll be another string under here. All we need is a handsome physics instructor to carry out this demonstration. So here's the bowling ball, and here are my strings. And I'm going to push down here, and you're going to tell me which string breaks first, okay? So if you think the upper string breaks, give it a round of applause. And if you think the lower string is going to break first, give it a round of applause. And if you think I'm going to break the opposite string of whatever you just said, give me a round of applause. Yeah, you're getting to know me. Okay, are you ready? Here goes. The upper string broke, didn't it? you know what I like to do? I like to repeat an experiment. Okay, there we go. Are you ready? 3, 2, 1. Oh, that time the lower string broke. But I played a little trick on you, didn't I? I told you I was going to repeat the experiment. But when you repeat an experiment, you have to do it exactly the same way each time, and I didn't do that. The first time, I pushed slowly. And when I push slow, the bottom string is only holding up the force that I'm pushing with. But the top string is holding up that force plus the weight of the bowling ball. It broke first. The second time I pushed fast, and that light string, kind of like an empty wagon, stretched a lot. But that force wasn't enough to move the bowling ball, so the upper string didn't stretch, and it was protected by the inertia of the bowling ball. Fun with inertia. What else? What else has inertia? Everything that has mass, including shopping carts. Let's take a look at this video from behind a Target store. Those shopping carts, they're sitting there kind of like plates and glasses on a table. Now that truck is moving kind of like a tablecloth. Where are they now? Pretty much in the same place, right? Just a little lower to the ground. Should we see that again? It says, those that do not remember their physics are condemned to do a lot of unnecessary work. So we are talking about inertia. Let's kind of summarize. First, before we do that, I want to show you, I want to convince you that you already knew about this before you came in today. Maybe you didn't know the name for it. But play along with me for a second. Well, you hold your hands out in front like this and pretend you have my cell phone in one hand and my wallet in the other hand. What can you do to tell me which one is heavier? What are you going to do to tell me which one is heavier? You know what I see right now? I see a lot of people doing this. You know why you're doing that? Because you know about inertia. You know that if you hold two things that are about the same weight, you'll never tell the difference. But the heavier one is going to resist changes in motion more. And if you shake them, you might be able to tell the difference. See, you knew about inertia. Maybe you didn't know the name of it, but now you do. A few years ago, we did inertia in our show, and my son, I think he was about 10 at the time, he saw the show. A couple of weeks later, we're eating pancakes. And you know how you use the side of your fork to cut a bite out of your pancake? Sometimes you don't cut through all the way, right? It's still attached. That happened to him. And he stuck that little piece with his fork, and he tugged it, and it broke free. And he said, "Dad, I used inertia to cut my pancake." Oh. As a physics instructor, there's no prouder moment. And of course, this stuff is all around us, right? We use it all the time. How do you get the ketchup, that last little bit of ketchup out of the bottle? You turn it upside down. You get the bottle moving really fast, and then you stop the bottle. And the ketchup inside wants to keep moving and ends up at the neck of the bottle. You get the ketchup out, right? And we talked about it already. It's why we wear seatbelts. And it's why the salsa ends up on your shirt when you're eating chips and salsa. That's right. Let's watch a slow motion video of me eating chips and salsa. Once it's moving in this direction, where's that going? It's not going down. It's got inertia. It's going to keep going, and it's going to end up on my shirt. That's right. Let's see that again. You can lean over all you want. It doesn't matter. Once it's moving horizontally, it's going to keep moving in that direction, And next time this happens to you, say, Mom, Dad, it's physics. The physics of inertia, it's all around us. Now, Galileo, lots of contributions to physics. One of those contributions is he did a lot of studying about the pendulum. Pendulum is something that swings back and forth. Have you been to the park recently and seen somebody swinging on the swings? That's a pendulum. And so the story is that Galileo was in church and he was looking at the chandeliers. And some of the chandeliers were just swinging a tiny bit back and forth. And some were swinging in a much bigger arc back and forth. Maybe they were in a breeze or something. And Galileo started to time them. And he was trying to figure out how much time it took to go back and forth. That's called the period of the pendulum, the time it takes to complete a cycle. And it seemed to him that the one that was barely moving at all took the same amount of time to complete a cycle as the one that was covering a big distance. He thought, how could that be? He went back and studied this. It turns out that's true. So let's take a look at the period of a pendulum. I've got some strings here. So there, these two, I'm going to do two that are the same first, hopefully. The same length, the same mass. We'll move them the same angle over, and I'll let them go, and hopefully they'll complete a cycle in the same amount of time. But I'm going to go 3 cycles. That way any small differences get exaggerated a little bit, okay? 1, 2, 3. Okay? So everything's the same, right? Now let's look at what Galileo thought. What Galileo saw was that one did a small arc like that, and one did a big arc like that, and they both took the same amount of time. You ready? 1, 2, 3. Same amount of time, right? And the reason is that the one that's a bigger angle, it's actually higher up. So it falls a bigger distance before it gets to the bottom, and it's going faster. And as long as these angles don't get too big, as long as they're relatively small angles, that greater speed makes up for the distance, and they both complete a cycle in the same amount of time. Isn't that neat? Now, let's change something. Let's change the mass. Let's see if the mass has any effect. I've got a big... We like bowling balls, don't we? This is a little tricky because you have to get the centers at just the right height, but I think I'm pretty close here. Okay, let's see if mass has any effect. 1, 2, 3. No effect, right? The mass doesn't matter either. Something must make a difference. Let's change the length of the string. So I've got a long string. I've got a short string. Okay, the short one is going to do that. The long one is going to do that. And let's see what happens. 1, 2, 3, 3. That makes a big difference, doesn't it? The length of the string. The longer that string, the longer the time it takes for that pendulum to complete a cycle. And now we're going to see a really cool demonstration where we change the length of the strings and get the pendula to make some really neat patterns. It's called a pendulum snake.
So, today we have the pendulum snake with us here at the physics show. And this is something that was built by our very own engineering club here at Foothill. And it essentially demonstrates exactly what Frank was talking about, that the length of a string on a pendulum changes the period, the speed of the period. So the shorter string gives us, over here, a cycle of 35 cycles per 50 seconds. Then it's 34, then 33, and so forth and so on until we get to the last one over here, which is about 17 cycles every 50 seconds. So when these guys gets released all at the same time, we get a very cool pattern due to the individual motion of every pendulum. You guys see why it's called the snake? So all the individual motions come together and they create these really, really cool patterns. They're kind of mesmerizing. And we know that we're hitting about halfway, 25 seconds, when they begin to actually split. See that? So there we go, we're at the halfway point. Now, again, the whole big picture can be kind of hypnotic. It's kind of hard to see the individual motion of each one of these, which is why we put a green ball right over here. So if you watch it, you can see it's just a very simple back and forth motion. And we're going to be hitting about the 50-second mark when you see these guys begin to coalesce back into one line. And then they start the cycle again. And that's our pendulum snake.
Isn't that lovely? Art and science coming together. David and I stand behind that curtain every time we watch it and ooh and ah about it. Okay. Galileo also did a lot of work with things that are dropping objects. And the old idea was you drop a heavy object and a light object, and the heavy one is going to fall at a faster rate and hit the ground first. And Galileo thought, well, if we could reduce the effect of air, these objects should drop at the same rate. His idea was they'd hit the ground at the same time. The story is he actually dropped objects off the Leaning Tower of Pisa. He was born in Pisa, Italy. I don't know if he actually dropped objects off the Leaning Tower, but it makes for a good story in physics class. So we're going to drop some objects here. I've got a heavy piece of wood and a light piece of paper, and I'm going to drop them. Which one's going to hit the ground first? The heavy wood. I don't even have to do it, do I? But I'm going to. 3, 2, 1. Okay. So what happened? The air got in the way, didn't it? And these two objects are about the same size, which means that as they fall, they're crashing into the same number of air molecules. So each one feels the same small force from the air. But like a light wagon, that small force had a big effect on the motion of this object, but the heavy object just fell, didn't really feel that small force at all, right? That's the inertia effect. So what we want to do is reduce the effect of air on the paper. How can we do that? I'm going to turn it into a paper airplane. This is my paper airplane right here. This will fly through the air better than any other paper airplane I could probably make. So, okay, so now it's tiny, right? It's still a light piece of paper. It's still a heavy piece of wood, but we've hopefully reduced the effect of air. And now let's see what happens. You ready? 3, 2, 1. Whoa, right? Pretty good. Pretty close, right? It looks like Galileo was right. So let's do this. This is also fun. We're going to take that piece of paper and we're going to put it underneath the wood. So the wood, what do you think? The wood's just going to push the paper down. They'll land at the same time. Let's see. Yeah, looks like that's what happened. Now what are we going to do? We're going to take that piece of paper. We're going to put it on top of the wood. What do you think? The wood's going to fall out from underneath and the paper will float down later? Shall we see? 3, 2, 1. Whoa. So what happened? The wood pushed the air out of the way. There was no air pushing on the paper, so it fell at the same rate as the wood. This, you should try at home.
So Galileo was working on this class of problems. You drop two things. Do they fall at the same rate? Do they hit the ground at the same time? And if you just drop two things, the answer is yes. So he began thinking about harder problems. Suppose one of them drops, but the other one's got some motion going left and right. How does that change the problem? Well, we've built a contraption that's going to test this. It's a spring-loaded rod, and one end is going to suspend a ball, and when we flip a switch, that rod is going to go, and the ball is just going to drop straight down. Meanwhile, we've got a target ball. And when we flip the switch, that rod is going to whack that ball, and it's going to go off in a curved path. The question is, will we have the same result? Will they hit the ground at the same time? Now I know at the physics show we love to count things down, but this one, we have to do it quiet. Because part of this is listening and seeing, do they hit the ground at the same time? So, 3, 2, 1. That sounded like the same time. But sometimes that's a little hard to hear. So we took a video. And here they are up at the top, and then we can drop them and they start going. Then we stop time, and they're at the same position. Then we stop time, they're at the same height again. And then they're going to go hit the ground at the exact same time. So what we're seeing here is that the motion left and right doesn't affect the result, that they take the same amount of time to drop. Now Galileo thought about even more interesting problems. And there was one that everybody likes so much, it ended up in every physics textbook ever written. It's got a special name. It's called Shoot the Monkey. What are they going to do to that monkey? The way I like to tell this story is that somewhere out in the jungle there's a sick monkey. But it's okay, there's a vet. The vet's going to go out, make the monkey all better. Now, I don't know what your experiences are with sick monkeys, but they are cranky, they are grumpy, and they bite. And I've seen enough movies to know that if you get bit by a sick monkey, that's bad news. But it's okay. The vet knows what she's doing. She's got a tranquilizer gun, so she's going to shoot the monkey. The monkey's going to get hit by the tranquilizer dart, fall asleep. Then the vet can take the monkey to the hospital without having to worry about being bitten, and then the monkey will get all better. So we've made our version. We've got a tranquilizer gun. Inside we've got a tennis ball. That's our dart. Up here we have a symbol. It's symbolizing the monkey. And you say, how do we know that that gun is aimed well at the symbol? Well, we've got a laser. And Frank is showing us that laser is going in a nice straight line. And if we look up at the symbol, we can see the laser is actually hitting the symbol. So now we need to put ourselves inside the brains of the monkey. I need to warn you, this monkey is not taking enough physics classes. Here's what the monkey is thinking. When I see the bullet come out of the gun, I'm going to let go of my branch. I'm going to drop out of that tree, and that bullet, which is traveling on a nice straight line, will go above my head. Frank, how's the monkey's plan going to work?
Well, the monkey has it half right. When the monkey lets go of that branch, it's going to fall. But what the monkey's not thinking about here is that the ball here coming out of the cannon is also under the influence of gravity. If there was no gravity, it would follow a straight line and end up at the top of the ladder where the symbol is now. But there is gravity. And as soon as it comes out of the cannon, it's going to be pulled to the earth by gravity, and it's going to follow a curved path. And by the time it gets to the ladder, it's going to be about where my hand is.
So if we think this through, either the vet doesn't understand physics either, or the vet really understands monkeys. We're going to count this one down. 3, 2, 1, fire. We can see that one again in slow motion.
So one problem that Galileo had, he's trying to do observations of falling objects. And I don't know if you've ever dropped something, but it hits the ground pretty quickly, doesn't it? Doesn't leave a lot of time to make calculations and observations. And so one of the things Galileo did was to, instead of dropping things straight down, he thought, well, maybe it would be the same thing if I let objects slide down very low friction ramps instead. Maybe that would be the same thing as dropping them, but everything would be happening slower. And he was right about that. He also did not have the ability to measure time very well. There were not very good timekeeping devices. But they did have good ways to measure weight. Right? Today we take that for granted. Everybody has in their pocket a stopwatch good to hundredths of a second, right? But what Galileo did is he slid cups in and out of a stream of water. And some of our students came in and replicated this. And then he weighed them because they had good ways to measure weight. And what our students are doing, they're just measuring the number of cycles, the time it takes to complete the cycles for the pendulum. 1 cycle, then 2, then 3. And hopefully this will fall on a nice straight line and show that Galileo was right, that this was a very clever way to get around that obstacle of not having a good timekeeping device. And that's exactly what they showed. So you got to be clever, right? When you have a roadblock, think of some clever way to get around it. And it works very well. We got a beautiful straight line there for the time for those cycles. That brings us to our next topic, temperature. Temperature tells us how much the atoms and molecules are moving that make up a substance. Everything is made up of atoms, right? They are the building blocks of matter. And they are tiny, tiny little things. You can't see them. In fact, the world's most powerful optical microscope cannot see them. They're too small. We need a special kind of microscope. We need an electron microscope to see them. If we could stack them on top of each other, 500,000 atoms, if we could stack them on top of each other, it would be the thickness of a sheet of paper. Okay, they are tiny, tiny little things. And they make up matter. They make up the clothes you're wearing, the seats you're sitting on. Even you and I are made up of atoms and molecules. And they are always wiggling. They're always vibrating, always wiggling around, not unlike some of you in your seats right now. Yeah. I like to use this analogy. Sometimes you kids are out on the playground, right? And you just stand still and talk to your friend. And sometimes you're out on the playground and you run around, you chase each other, right? It's the same with physics students and physics instructors. Who has more energy, the kids running around or the kids standing still? The kids running around, right? Who gets hotter? The kids running around. Who takes up more space on the playground? The kids running around. It's the same with atoms and molecules. Thank you. Woo! You add more heat, those atoms and molecules vibrate more, right? And when they bump into each other, they hit each other a little harder. They need a little more elbow room. Almost universally, when you warm something up, it expands and takes up more space. There's always an exception, isn't there? But almost universally, you warm something up, the atoms and molecules wiggle more, they need more elbow room, they take up more space. Let's see what happens to a solid object like a wire when we heat it up.
So, as we get set up here, how many of you had toast this morning for breakfast? When you looked inside your toaster, did you see a whole bunch of little red lines and such? Yeah? Well, what's happening within your toaster, what your toaster is doing, is it's sending electricity through a bunch of wires. These wires, they get all hot and they start heating up and they glow red hot and they toast your bread. So, we have a wire here that works on a very, very similar principle. And Haley here is going to explain it to us.
So I have it hooked up to some electricity, and we know that electricity makes it hot because that's how we have toast. We also know that when things get hot, they get bigger. It's attached to the ends, so it can't get bigger this way. It's going to droop down. That's why we have these little pieces of paper here. So when I turn up the electricity, it sinks down really quick, huh? It's getting bigger.
But how do we know that this is hot, Haley?
We could probably touch it, right? We could lick it.
No, never ever lick your science experiments. If there's one thing you take from this show, don't ever do it. It's going to end poorly, believe me. So instead, I'm thinking that we just turn up the heat a little bit and watch what happens to the paper. You guys see that?
Pretty hot, right? So, no fires. Let's not get in trouble here. And as I'm turning off the electricity, I'm still burning some paper, but you can see the wire coming back up because it's getting smaller again as it cools back down.
Paper is definitely hot right over here. And that right there is thermal expansion of a wire.
So they just showed us thermal expansion of a solid. They heated something up, it got bigger. What we're going to do next is thermal expansion of a liquid. We're going to heat it up and it's going to get bigger. But sometimes that's a little hard to see. So what we're going to do is we're going to use the concept of floating to help us out. Now, suppose right after the physics show, you all went off to the swimming pool, and you had a little brother or sister, and they don't swim very well. What could you put on them to help keep them safe? Yeah, floaties, those little balloony things. And what they do is they make you less dense than water, and so you float. Now, suppose you were being naughty, and instead of giving them floaties, you just gave them some bricks, and then you toss them into the swimming pool. What's going to happen? Yeah, they're going to sink right to the bottom. Do not try that at home. They're going to sink to the bottom because now they're more dense than the water. The denser the water is, the easier it is for you to float. So when you're in fresh water, it's not very dense, kind of hard for you to float. You go to the ocean, salt water, a little easier to float. If you go to the Dead Sea, very, very dense water, it's very easy to float. So we can look at our instrument here. This is called a Galileo thermometer. And we can see that some of these balls are floating. They're less dense than the liquid around them. And some of them have sunk to the bottom. They're more dense than the liquid around them. So less dense, more dense. Now I've got a hairdryer. And you're kind of looking at me saying, David, you don't need a hairdryer. Well, not for my hair, I don't. But this is a pretty good source of heat. And what I'm going to do is I'm going to put it here. And we're going to start heating up the water. And now we have to remember what happened to that wire when we heated it up. Well, that wire expanded. It took up more space. Now we're heating up the water. It's taking up more space. But that doesn't mean we've got any more water, any less water. We've got the same amount of water. But if you've got the same amount of water, and it's taking up more space, that means the water is getting less dense. Well, what we can remember is that the denser the water is, the easier it is to float, and the less dense it is, the easier it is to sink. So what we can see here is these top three balls that were floating at the beginning, they're starting to move down. They're sinking. Why are they sinking? Because the water's getting less dense. Why is the water getting less dense? The water's getting less dense because it's expanding. Why is it expanding? Because it's hotter. Thermal expansion of a liquid.
So we've talked about solid objects. We showed you a wire. Other solid objects, bridges. We have a few of those in the Bay Area, don't we? I am told the Golden Gate Bridge is about 1 meter longer in the summertime than it is in the wintertime. What's a meter? About that much, right? A meter longer in the summertime. So engineers have to take this into account. They design these expansion joints into the bridge so the bridge can expand and contract and it stays safe. We can drive over it. David showed you a liquid. That's how a lot of our thermometers work, right? The red liquid in the thermometer, it warms up. The atoms and molecules move more. They bang into each other a little harder. They need more elbow room. They push their way higher up. We read a higher temperature. I like to say it's like this. If we took all you kids and put you on a dance floor and the music was nice and low, you're dancing, maybe we can fit you on the dance floor, right? But we crank up the music and you start jumping around and swinging your arms, and what happens? We need a bigger dance floor, don't we? That's the same thing here. Now let's see what happens to a gas like the air in this room when it's in a balloon. So we're gonna make those balloons really cold using liquid nitrogen, and then we're going to let them warm back up. I'll tell you more about liquid nitrogen in a minute, but right now all you have to know is that it's really, really cold. About negative 200 degrees Celsius, about negative 320 degrees Fahrenheit. Okay, so I've got some balloons here. You think they're going to fit in my bucket? Okay, I've got some more balloons. Are they going to fit? I've got some more balloons. Are they going to fit? What must be happening to those balloons for all of them to fit? They must be getting smaller. They must be shrinking. So now, that's because they're really cold. Now we're going to take them out and let them warm back up. Lost one. So almost universally, right? There's always an exception, but almost universally, gases, liquids, solids, you warm them up, they expand, you cool them down, they shrink. Thermal expansion. So other fun things happen when you cool them down and warm them up, right? Here I have a bouncy rubber ball. It's bouncy and soft. And I'm going to make it cold, and then we'll see what happens. Maybe you've done this at home. Have you done this with a piece of bread? At home with some bread, and you put it in the freezer, and you take it out of the freezer, and because all the atoms and molecules, they slow down a little bit, they can hold on to each other in a much more rigid way, right? And the bread becomes very brittle. So we'll see what happens to the rubber ball here in a minute. But now let me tell you about this stuff. This is liquid nitrogen. The air in this room that we're breathing is mostly nitrogen. It's about 80% nitrogen, 20% oxygen, which we need, right? And there's also some moisture, a little bit of water in the air. And if you start with a solid object, the atoms and molecules are holding on to each other in a very rigid way, right? That makes a solid. But they're still vibrating. And you add a little energy, you heat it up a little bit, and now they're vibrating more. They're still holding on to each other in that rigid way that makes a solid, but they're vibrating a little bit more. And you add a little bit more energy, and they start vibrating more. And pretty soon they kind of break free from each other, that rigid way they have of holding on to each other, but they have a long, loose way of holding on to each other. That's a liquid. And you add a little more energy, and they start vibrating more, and pretty soon you've got it hot enough. They're vibrating so much they break free from each other. They cannot hold on to each other at all. They are independent of one another. That's a gas. I like to say it's like this. If you're jumping on a trampoline with your friend and you're trying to hold hands, if you're just doing small jumps, you can hold hands, no problem. But you start making some big jumps, and pretty soon you have to let go of each other, right? And that's what happens here. So the air in this room has some moisture, some water molecules in it, but they're whizzing by each other so fast they can't grab onto each other. But look what's happening right here around the bucket. It's very cold right here. And so the water molecules come into this cold region, and they lose some energy, and they slow down, and they can grab onto each other and make these little droplets here. That's called condensation. So sometimes on the outside of a cold glass, you get some water forming, right? Because that's the moisture from the air condensing. Okay, I think that rubber ball is about ready. Shall we take a look? I have to put on a big, heavy glove to protect my hand, because when you touch something that's very cold, it's like touching something that's very hot. You damage your skin. You burn your skin. Okay, so that rubber ball shattered. It's very brittle, right? Like the bread coming out of the freezer. And if I wait long enough, those rubber pieces will warm back up, and they'll be soft and pliable again. But they won't be a ball again, will they? No. In fact, you know what I'm going to do? I'm going to take some of those pieces and put them in some warm water, and then I'll show you that they are soft and rubbery again in a minute. Okay, I think we're done with this now, right? Am I forgetting something? Is there a banana in there? Well, let's see. That banana, which is normally a nice soft thing, right, is going to be frozen hard. So what kind of tool is hard. Can you think of a tool? A hammer, yeah. So let's get a nail out, and we'll try to use that banana to hammer that nail. Okay. This is one of those demonstrations you want to clean up while the banana is still frozen. Now, if I wait long enough, it takes a long time for that banana to thaw back out again, but if I wait long enough, I could eat that banana. Okay, one of the things that I think about with temperature is thermal conductivity. How does heat move from one place to another in a solid? If I had a metal rod in front of me here, and that rod was all the same temperature, all the atoms and molecules that make up that rod would be vibrating at about the same rate. And if I held a match under one end, the atoms and molecules right there would gain some energy and start vibrating more. But because they're all holding on to each other, they'd get their neighbors. They'd be pulling on their neighbors and get their neighbors to vibrate more. And then their neighbors would get their neighbors to vibrate more. And pretty soon, all the atoms and molecules would be vibrating more, which means the whole rod would be hotter. That's how heat temperature moves. Heat moves through a solid. And there's I'm reminded of this in the morning when I get out of bed. Because I step on the carpet, not so bad, right? I walk around to the bathroom, I step on the tile, brrr, right now I'm awake. Why do they feel so different? The carpet and the tile in my house in the morning are all the same temperature. It's because heat wants to flow from hot to cold. Heat always flows from hot to cold. And when I get out of bed in the morning, my feet are toasty warm. They're the hot object. I step on the carpet. The heat wants to go out of my foot into the carpet, but it gets stuck. It can't move through the carpet. It's a poor thermal conductor, so it stays in my foot. I step on the tile. The heat goes out and moves away because the tile is a good thermal conductor, and more heat comes out and moves away. So my foot loses a lot of its heat, and the tile feels cold. There's a very dramatic demonstration maybe you've seen where they spread out white-hot coals, 2,000-degree coals, and walk across them with bare feet. You ever seen that? The theater wouldn't let me do that for you. I'm sorry. But I'm going to do something similar. Those coals are chosen very carefully. They're very poor conductors of heat. They're very porous. That means there's lots of little air pockets like a sponge, and they're very poor conductors of heat. So when your foot goes on them, the heat wants to go into your foot and burn your foot, but it can't move through those coals very well. So as long as you don't stand there for more than a few seconds and get off, you're okay. You would never step on a good thermal conductor like a piece of metal that was that temperature. No, it would be the last thing you ever stepped on. Yeah, that would be bad. Okay, so we're going to use a graham cracker. A graham cracker is very porous. It's a very poor thermal conductor. I'm going to make it really cold. And I told you that if you touch something that's really cold, it's dangerous, right? So I'll show you that as long as I keep moving it around, I'll be okay here. Are you ready? I guess the question is, am I ready? Thermal conductivity. Now let's take a look at some of the rubber pieces. They've thawed out now, nice and soft and rubbery, just like we expected. Okay, I think we're done with this, so we're going to have a little fun with the leftover liquid nitrogen. To summarize, we've been talking about temperature, we've been talking about thermal expansion. That's how a lot of our thermometers work. We've talked about bridges and other things. The engineers have to take this into account when they design products, right? What is this? This is a filling in a tooth. That's a different material than the tooth. Sometimes we drink cold drinks, sometimes we drink hot drinks. I hope an engineer tested that to make sure it expands and contracts at the same rate as my tooth, or I might be in a lot of trouble. Have you sat on bleachers like this at the park? What happens? Let's ask Mom and Dad. You get cold sitting on those, don't you? Yeah, because aluminum is a very good conductor of heat. The heat from your body goes out and moves away. More heat goes out and moves away. You would be much more comfortable from a temperature perspective sitting on wooden bleachers. And this high-tech device, a frying pan, a little bit of physics there. The bottom of that frying pan, you want to be a really good thermal conductor so your food cooks evenly. But there's something on that frying pan you want to be a really poor thermal conductor. The handle, right? You don't want that to get hot. The physics of temperature all around us in our everyday lives. And that brings us to our last topic of the day, pressure. We're going to start off with a quick atmospheric pressure demonstration. Atmospheric pressure is caused by the weight of all the molecules in the atmosphere being held to the Earth by gravity. Okay? The Earth's atmosphere, the air around us, being held to the Earth by gravity, pushing down on us. Can you feel it? No, you can't feel it, right? Because it's pushing on every side of us. We don't notice it. But interesting things happen when we can remove atmospheric pressure from one side of an object or add extra pressure to one side. And what we're going to do, we're going to add some extra pressure to one side of a t-shirt using a t-shirt cannon. So we'll put a t-shirt in there. And we'll pump up the other side. So what we've got here is a t-shirt in here, and there's atmospheric pressure pushing on this side, and we have 2 times atmospheric pressure on the other side. Olga's going to release that pressure here in a second, and we'll see what happens. We've got another t-shirt here. This time we'll do 3 times atmospheric pressure. We've got one more t-shirt. This time we'll do 4 times atmospheric pressure. If you didn't get a t-shirt, have no fear, they're for sale in the lobby. If you're like me, and I know I am, you're wondering what we do with the money that comes in from ticket sales, from t-shirt sales, from donations. We think we're doing a lot of good things for physics education in Northern California, but by far the biggest and best thing we do, about 3/4 of our budget, we bring Title I schools in, schools from low economic areas, and we put on the physics show for them. Some of the teachers tell me this is the only field trip they're going on this year. They just don't have a budget for it. We pay for the buses. we put on the physics show. The kids get a tour of our beautiful campus. They even get a physics show T-shirt. And as David likes to say, they all leave with the T-shirt with the name of a college on it, and that T-shirt doesn't have anything to do with sports. This is a time lapse of one day. We did 5 days just like that. About 4,000 kids came here. We want to thank you for making that possible. So we started to talk about pressure, but we never defined pressure for you. We have to tell you what that is, right? Pressure is a force per unit area. What does that mean? It means if you're running around the house and you bump into the side of the table, yeah, not so bad. But if you bump into the corner of the table, ow, that feels different, right? That's pressure. If David pushes on me with his open palm, not so bad. If he pushes on me with the same force with the tip of a needle, ow, right? That's pressure. That feels very different. Maybe you've seen somebody chopping vegetables in the kitchen. If the knife is nice and sharp, the force is concentrated on a very small area, and it goes right through the food, right? And if that knife is dull, the same force spread over a larger area, it doesn't have the same effect on the food. That's pressure. And we're going to do a little demonstration with two of our favorite things.
Balloons?
And nails.
Best friends forever. We're going to balance that balloon.
On two nails.
I'm going to put my hands on my ears. We're going to repeat the experiment. This time we're going to balance it on 2 rows of nails. And I know what you're thinking. More nails means more holes, means it's going to pop even faster, right? No? Well, let's find out. That's 1 weight. That's 2 weights. That's 3 weights. That's 4 weights. That's 5 weights. That's 6 weights. We're all done waiting. Hey, Frank, did you bring your indestructible balloon to the physics show today?
Sometimes I'm tricky.
Kids, is there any way we could tell whether or not Frank brought his indestructible balloon? Put it on the first 2 nails? Oh, Frank, we've got a sharp crowd with us today.
Ah! Just the threat of putting the weight on was enough to pop it. It appears the number of nails makes a difference. If we put a balloon on 2 nails and we tried to put 20 pounds of weight on top, each nail would have to push with the force of 10 pounds to hold up its share. But if there are 20 nails and we put 20 pounds of weight on top, each one only has to push with the force of 1 pound to hold up its share of the weight. The more nails there are, the less each one has to push to hold up its share of the weight.
So, Frank, let me see if I've got this right. If I put a balloon on 2 nails,
bad news for the balloon.
But if I put a balloon on a whole bunch of nails?
Yeah, not so bad.
Frank, does this work for things that aren't balloons?
It does. Even physics instructors.
Oh, Frank, if I put a physics instructor on 2 nails?
Oh, bad news for the physics instructor.
But if I put a physics instructor on a whole bed of nails?
Let's see what happens.
Jumping up and down on a bed of nails I lie on.
Frank reminded me to put on my safety glasses. He doesn't want anybody to get hurt. You can see what we're doing here, right? There's a bed of nails underneath him, and there's a bed of nails on top of him. We've carefully balanced a cinder block, and I've got a sledgehammer. Frank, are you okay?
No leaks.
Now, there's a lot of physics keeping Frank safe. It's not just top quality equipment. The first thing that I think about is that Frank, he's kind of like a big balloon. If we put Frank on 2 nails, that would have been bad news for Frank. But we put Frank on about 800 nails, so each nail only has to push up with a tiny amount of force to support his weight and all of the weight on top of him. The second thing I think about is the hammer and anvil demonstration we did earlier in the show. The anvil, because it had inertia, protected Haley's hand. The same way, the top bed of nails and the cinder block, they had inertia. They were at rest. They wanted to stay at rest, even though the sledgehammer wanted to make them move. And then finally, the sledgehammer, that had all kinds of energy as it was going through the air. But a lot of that energy goes into busting up the cinder block. So there's just a lot of great physics in that demonstration, and it's just a fun way for us to end our show.
Today we talked about inertia, temperature, and pressure. Those are all topics under physics. Physics is part of science. Did you have fun? Foothill physics instructor David Marasco. Our students, Haley Miller, Olga Kritova. Behind the scenes, we have a lot of students, Samuel Arnold, Colin Arnold, Mami Harakawa, Melody Bake. I'm Frank Coscarano. Thank you for coming. We'll see you next year at the Physics Show.